what we will do today, so first we will do our own data set. So that's very interesting. It is very good to learn and to get a view on how the forest look like that I'm extracting first with the simulation tool. This is also available in PolSARpro, and then you can use this data actually because you know exactly how this forest look like and can try to invert it. And you can immediately see how good are the models that are implemented in PolSARpro in order to invert height. And so therefore, I think this is really a very nice tool where you can do the first investigation and also the first data processing directly on your own generated data. So what I was doing also, so the first I will explain you how the simulation tool works. But what I have also done is in the folders, you have already a master and a slave file, and you have an RGB image where you can have a look how this forest look like that I have generated. So this is really something that you couldn't have a look. And I've done it for a deciduous forest. And I was generating also my forest in this PolSARproSIM, so which is a very great thing. So the second thing that you should do then is to generate complex coherences. The interferometric coherences that we have seen already today. So this is what you will generate it, you will display them, and you can do also first interpretation out of it. Then we will do to the interferometry to remove the flat earth. So this is something that we have learned also today. This is the flat earth is in principle the regular frequency of the interference that are appearing when you have a flat terrain, and this is something that needs to be removed in order to have the visibility of the topography. So this is something that you will do also for this forest part estimation, because this flat earth removal, it's always needed in any kind of interferometric images. Okay, and then you can renew the generation of the complex coherences, and you can again have a look here. So first normal complex coherences, and you do removal of flat earth, and then you can again display them. And then we will go more to this interferometric coherence generation at different polarizations. So our Pol-InSAR model, in principle, our Pol-InSAR data that we use here, you can do, if you like, different approaches. You can use a linear polarization coherence and optimized, and you can display and interpret them again. Then we will have a section, which is the main section, is the estimation of volume height in this case. So using models in order to estimate volume height. The first one is using the interferometric phase. So this is something that we have used also as a very example in the beginning, where you say use just interferometric phase center height, then you use the coherence approach. You can do some analysis out of it. There are some analysis tools that you could use with PolSARpro. And you can also do some statistical analysis of it, and then you can compare the different different results with each other. Okay, let us go directly to the PolSARpro biomass. I mean, I think edition version 6, I think I do not need to say a lot about it because you have worked now with this PolSARpro tool already. So that's the thing that we have done. And I'm very grateful to Eric that he was taking so much effort to develop this tool and to implement all the algorithm that we have developed in order to make it more easier for you to just push the button and it's already in principle running. So, but if you like, and probably also Eric was explaining it, you can also look to the code and you can implement it by yourself in your kind of software program that you have. So that's also possible. So both things are very useful here. Okay, what I like to say that for sure, also for this Pol-InSAR training, there's a training document also in PolSARpro, which you can use. This one is from Shane Cloud, which is very useful, and then you can use them in order to do also your own tutorial later on if you like. So this is also a very nice tutorial explained. So it's really recommended to do this. Okay, let us go now directly to the simulation tools that we have. So this has been developed by Mark Williams. I'm not sure if Eric was already mentioning this. So that's a very nice tool where you can, in principle, derive polarimetric and interferometric data out of it, doing this simulation of a forest. This is the tool that you see. In principle, you just go to utilities. You open up the PolSARproSIM, which is a simulation tool. You go then to this part, which is called forest, and then you get, in principle, this display or something similar. And here now you can configure your own forest. That's very interesting. You can define the geometries of the system that you are running. And you can put also the system configuration in terms of frequency. In this case, it is an L-band system, therefore 1.3 gigahertz. You can define your ground surface contribution with roughness, wetness, and so on. So it's really great, and also slopes. And then you can do your forest configuration on this part with the tree species, tree height that you set up, also the density of a forest. That's very important. And then what you could do is just a safe configuration. You can also define, in principle, this is then given, define the number of and rows, so how big you like to have your scene. And then you will have, in principle, a configuration file, which is called PSPSIM config. And this is then storing actually the configuration that you set here. And what you get out are the scattering matrix actually on this forest in master and slave, so in the interferometric possibility. And this is also the data that you have already now in the in the folder. It's called master and it's called slave. Master always means the first acquisition, and the second acquisition is actually then the slave. So you have these two acquisitions where both it's represented by the scattering matrix actually. And it has an absolute phase so that you could do also interferometry out of it. So therefore, this is a very nice tool, and you can do any kind of forest out of it in order to explain it. So that's a little bit much better explanation. But as I was saying, you can also go here into it to get more knowledge about it. It's there's also more explanation from Mark Williams on the model itself. So here's only a very simplified version of what you can do. What he's doing mainly, he's configuring different forest types, for example, pine and deciduous forest, as you see here. He's defining certain scattering mechanism. For example, we have the direct ground, direct volume, and ground volume contribution. This is very important between with both trees and short vegetation comprising volume terms. So what you can also do, sorry, I was not mentioning, you can also do very kind of bushes. So it's not really agriculture, but you could simulate, if you like, and with bushes also agriculture crops. So very short vegetation, and you could also do kind of simulation with it just to get a knowledge about it. Okay, and that's in principle, this is in principle the main idea about what you could do here with the forest. And at the end, what you get is a kind of simulation part here, where you get then this interferometric and polarimetric observables out of it. So this is a hedge where I was talking about, like a bush where you have also very short vegetation and the random contribution, random volume contribution, so that you could potentially also simulate, I would say, agriculture trees. Okay, that's what can be done. These are my parameters, therefore they are in the slides that I was filling here for my kind of simulation tools, and therefore you could use the same, as I was saying, the data already available, so you don't need to run it, but you can also run it. It's just up to you how you do this. And in principle, what we have here is, as I was saying, is a forest height of around 18 meter. Is a deciduous forest with a quite strong density of 300 stems per hectare. I mean, it's a kind of natural forest in these Middle European regions. with low soil moisture, so that we do not have a storm effect here in smooth surfaces, and a spatial resolution of 1.5 to 1 meter around. Okay, the next step would then be, and this is what you know already also from the lecture of Eric, is in principle that you define your data set. In this case, what you can do with a single baseline, you do dual data sets here, where you have again the master and the slave when you have generated them, or you use my one. Then you can go further on, where you need to, in principle, configure main data directory. So don't take the directory that I have here or these ones. So you need to define, in principle, your own directories, because otherwise it will not work. This is probably quite clear. Okay, if you have done all this thing, then the main processes that we were looking for is this InSAR functionality. I think that's more important. And for this InSAR functionalities, it's clear here you have one box, which is very important, where you can do the flat earth removal and the flat earth estimation. What you also need is to do a co-registration of these two images. So first co-register them and then do flat earth estimation and removal. That's important. You could do, if you like, a speckle filtering. That's possible, but it's not needed for this kind of data that you have here. Okay, this is not what we will use. We will use now the Pol-InSAR functionality, which is mainly to do an interferogram estimation, coherence estimation, and doing also coherence analysis. And the coherence analysis is very great to do it in this complex plane, which is a unit circle, and you can do also kind of coherence region estimation. So that's also possible if you do it in this area. Then you have this functionality 2, which is in principle now our inversions. So first is the coherence estimation, interferometric coherence estimation, and then you can work on the forest height estimation and vegetation height. And also here you see it's also implemented as a polarization coherence tomography. And to do some analysis is what I was saying. It's good to do sometimes to stop and do an interpretation and think about it. What is the result out of, and if they make sense. Sometimes can happen that there's some functionality which we do erroneously, and then it can make, in principle, also no sense to have them. So therefore, sometimes it's good to make a break in this process of this analysis, and then to look at in this tools which we have for histogram profiles and so on, which are quite important to work with it. Okay, if you go forward, yes, so what we first have is matrix element masters. This is what we can estimate. You know this already also from Eric's course. You can here now define in principle your, or you can generate a scattering matrix of the master. That's clear. You could do this either using now the different scattering values. I've done it here in dBs now, just located them, but you can also define them separately as you like in the scattering matrix. I've done then the display with GIMP. That's also implemented. This is my simulated forest that you can see, and these are the different, this is the scattering matrix that I get out of my master. With S11, S12, S21, and S22. And this is an RGB image seen here of this. You see we have some shadow. We have here really a forest part, which is quite interesting. And this is my main result out of it. So what I would do then is in principle to go to the coherence estimation. I think that's very interesting. When you go to coherence estimation, you can follow up here this part. You should define the directory of the output master. So that's very important if you go to coherence estimation. And then you can define either you do a linear coherence estimation with HH, HV, VV, or you do a different other polarization basis. It's also possible using left-left or left-right or right-right circular polarizations. You need also to define your window. That's important. And in order to see then what you got out of it, you can here tick the BMF file. So, and always note that the output directory is automatically then set here to the track master, track slave file. So that's a new directory that is built up. These are my results that I got, which you will also get if you take the same data set. Otherwise, they look a little bit differently from the forest type, but these are now the coherences at different polarizations. And this is the phases, so the complex value. So you see the coherence phase, interferometric phase, where you still see, and that's very interesting to see the flat Earth contribution, right? This was the very regular frequency that you have over from near range to far range over the scene. So this is what can be seen. The coherences are quite high, specifically for sure on the surrounding where we have high coherences, and then a small volume decorrelation over the forest itself. Okay, when you like to go to display, you know, you can in principle use this display feature where you can derive also BMP files if you have not ticked beforehand the BMP button before. This one, I'm just going back here. This one, if you have not done this, then anyway you get the information, you get the files out, and you can still do your own BMP file. This is just to mention that this is always possible using then the data that you would like to do. Okay, and then it's about the flat Earth removal. So in principle, what you do, you try to get the flat Earth removal, where you take in principle the you have again a new, let me say, you first estimate it, and then in principle what you do, you try to display it. This is what we like to do here. You go back to the feature and you do an estimation of the flat Earth. You get the bin file, and the bin file, what you could do then later on is to derive here a BMP file so that you get also a visual view on the flat Earth. And I show this here. So this is now the flat Earth just estimated in terms of this fringe pattern, as I was just mentioning in the lecture. Okay, going forward on, this was this flat Earth estimation, and then actually the removal. So this is what we have just done. So in order to do this by yourself, you will see it, I think, already also in the master in the master file, but I think it's good to do it by yourself. And this is what you can do here. You just have then the master and the slave, and you get in principle this flat Earth bin then out. This is the file that we have displayed beforehand. This is what we like to get. This is just considered to have a real, so in radians, the file ticked on. You can tick on symmetrization, conjugate, and then in principle you get it in the new folder, which is called slave flat Earth removal. Okay, going further, then you can do a second time the estimation of the interferometric coherence. This is normal as we have done before. You could also take in principle the Pauli images, so that you have also the Pauli images available. And if you like, you can also do here an SVD optimal estimation. But I think the most important now is the linear and the circular one. So the bluish one is not so important, but could be done. So now we have the corrected interferometric phases here without any more the flat Earth. So it has been removed. And now you see the coherence phase that you see here with the height. So it's still now in degree because it's a phase. You see the variance in degree. The greenish one is a 0 degree. So this is really the flat, the principle, the zero height. And everything that is now yellow, orange, and going a little bit into the red is in principle our height estimate. If I go further on, you can now display the coherence magnitude in terms of with the basis of a linear basis and the left-right circular basis, if you like. So that's possible, and then you can compare both of them. And you see already there some smaller differences in terms of coherences. You see here the left-right, we have this very strong decorrelation, stronger than in principle here in HV, which would be the one which would be also interesting. Whereas the strongest decorrelation or stronger decorrelation is also in the right and also left circular polarization defined. Okay, you could also do, this optional, you can do also the optimized coherences. I was not talking about this here, but in the literature you find very often optimization processes, how to do the best stretch actually in terms of coherence between different polarization. This is done here, and you see already also the white area here, this white area has a little bit this pixeling things, which is probably not very nice, because this one has a little bit a problem in terms of having a right estimation of the ground. Okay, if you have done this, you go further in this PolINSAR functionality for one, and then you can do the first one, also the coherence analysis in terms of complex plane estimation. What is popping up is in principle this complex plane plot here, where you can define the polarization that you would like to see. You need to have an average size here that you define, or you can also define an area if you like. So what you do, you have here in principle kind of a plot where you can, when you go with the cursor around, you can define this exactly the area or the position of the mouse where you in principle get the either pixel-wise an estimate of the coherence plane, or what you can, this would be the point-wise, or you do it area-wise, so that you define an area in this region in order to have then the estimate of the interferometric coherences in the complex plane, so unit circle. This is what is getting out, the unit circle estimate. So here you see for different polarizations, I have now here the coherence complex plane in my unit circle. I was doing this for 3 different regions, as you could say, and you see already you could have some kind of regions. You can also have here only, this is only over the ground, for example. This is here in the middle of the volume that I have done, and here even I've done it in a different part of the volume. So therefore, you see you could have really differences in terms of regions of interest in the forest image that you have for the forest data that you have for this for the interferometric coherences at different polarizations. Good. The next step is then, if we do a little bit the interpretation of a complex plane and you have estimated this, you could do then the forest height inversion. Use the inversion procedure, which is in principle this one. Here, what you could do, these are different kind of forest height estimate programs. We have the one which is called Polarimetric phase center height estimation, where you can also choose a channel, which one you like to do. So that's a normal phase center height. Then you have a dam differencing algorithm. You have a coherence amplitude inversion process. And you have a ground phase estimation of the random volume over ground inversion procedure. This is the one that I have mainly now explained in my lecture to you in order to understand what you get here. And here you can even define the polarization for the top phase center, or you can also define the polarization for the ground phase. So that's also possible. Okay, here's again a short explanation of these different approaches that you have for the random volume over ground. This is the one that I have already explained. The coherence height is it's based on the amplitude inversion, right? And the assumption only volume scattering is present, which means it's a 2-dimensional system here. We have in principle no ground. And you can do, in this case, the inversion according a sinc function, which is a very, very simple assumption of the f of z in this case. The phase center heights is what I was saying already, is just a height, the phase center height estimation. We have just looked for the phase center heights. And then there's another approach, which is called dam differencing heights. It's based on the difference of 2 polarization channel with different phase location between volume and ground. So in principle, what you could choose is you could choose in principle two polarization where you think this has the highest difference between each other, and this in principle is then estimated as a Dem difference height. Okay, these are the method that has been used here. Yeah, I would think I would not go again through. This is what you have learned already. This is this random volume over ground approach that we have used. And okay, what you could do now is in principle you could start to work on it and do it by yourself. So for example, the phase center height, what you could do is starting actually with HH polarization. This was one idea, but you can also use any kind of polarization bases in order to fill here to see what is the difference. So that's very interesting also to see, just to get a feeling what is it different and what is the best polarization basis actually for my forest to be estimated. Yes, this is what you could do, and this is what is coming out then out of this different polarization combination that are available. It's up to you to choose which one and then also to do some interpretation out of it. Then what you could also do is to do a little bit you could do some histograms in this, or compare the phase center height statistics in this case. This is what you could do. And therefore here, this is a statistic program that you have below where this plot is opening up here, and you could, with the cursor that you have here, following the cursor in this popping up image that you have beside, you can see then exactly which kind of volumes do you get, and you could then, this is a float value now in the moment with real values, but you can also do a modulus or any kind of other experiment just to get a histogram about this area. Right, what you could do, I mean, do it by yourself. So the first one was really select a BMP file. The second step is select an input binary data file, select what to show, enter the histogram title and histogram label if you like, and what you get out is actually then the differences that you have here. You can then define a polygon area, so an area of interest in order to do the statistical analysis by selecting right or left button, right, and enter and close right button. So there's some things that you could do by yourself. And then at the end, extract and process, and you can come up with a histogram. The histogram should then look like this. For example, for this area of interest that you have chosen here, you can in principle plot then the histogram, which is showing you some labels on some value, depending what you have ticked here. In this case, it's a float parameter. Yes, what you can also extract it into GIMP if you like. So like this, you can also store this image and save it for you, for your, for any kind of purposes. Okay, you can do this for all the other things too. I've done it now here for the phase center heights, where I've generated these plots and the histograms of the phase center heights in order to see what are the height values of the different polarizations. And you see, I mean, this is just a kind of profile over it. So we have a lot of values which are around, it's not a profile, it's a histogram, sorry, where you have a lot of value around 0, right? The zeros are the blue areas here. And then you have, in principle, some higher heights until around 50 meter. If you remember, my forest height has been estimated to be 18 meters. And then you see also here the diversity in VV. You see here BAM, that's quite interesting. And the same, you see also a higher contribution in terms of histogram, also in HV in this area around 15 meters, and the same is actually for VV. So that's quite interesting. So you see, but with the phase center height, you get a little bit a kind of let me say, you don't get really 18 meter, but an underestimation of the heights. So that's what it happens. Okay. Okay, what I was doing then, so yeah, in principle, this is an explanation. Primarily ground contribution is HH, therefore you have here this lower estimate, so lower values and not so much higher values, which you have here much more in terms of histogram, a lot of the values which are around 0, and this should be the primary why this is here a bump, because this provides you primarily the volume contribution for the phase center heights. Okay, the further on you can do it in left, left, right, right, and left, right, in any kind of polarization states. You can also do it in this optimized polarization. This is something that we had already, which you could just explore and investigate. Okay, I would go now just further on. What is the next? What you could do? Please generate the following product, compare the different inversion models in terms of height inversion. So this is now the inversion models itself that you could use. Here the DEM, the coherence, the ground phase estimation, that's important. These are all that you can tick and define also. What I've done, just very to have a brief summary of it, I've done this now for each of these different methods, and you get the different results out of it here, as seen here. You have this random volume over ground, where you have a certain range of, in principle, certain range of height. This is what we also expect. But you see really there's already quite strong differences, having the same forest type, the same input parameter, but the models providing you really differences, strong difference in terms of forest height estimation. In order to really know which kind of values are behind now this very colorful images and differences here, you could again do also kind of histograms so that you're clear what you can see. This is a random volume over ground inversion, as I was saying, so it should have the highest, in principle, kind of values for the forest height should be 18 meter. This is our reference, and you see we have around this 18, yeah, this is here, this is 20, around this 18, we have the highest values also in terms of the histogram. So it seems already that it fits quite well here. This is a coherence height that you see here with this amplitude. Yeah, our highest heights in principle, just Google. So these are the highest terms of histograms, so in terms of numbers of samples, it's here quite high, but you have also higher heights. So that's something that you see here very well. Here our highest samples, it's more again, the ground has the highest samples, and then it's going down in terms of height that you see here. It's quite interesting. It has a different, completely different, I would say different behavior as the first one. If you go now to the phase center heights, you have two bumps here that you can see very well. So the terms of heights, you have quite a lot of heights between this 14 to 12 meter height, and then also quite a bump over this between 0 and 2 meters. So it's also quite interesting in terms of labeling. And this is a DEM difference in height. Again, also over for 0, it's quite strong, kind of high amount of samples over this area, and then going down in terms of samples until the 12 meters. So you have here a strong underestimation also of the real height using the DEM differences. Okay, yeah, that's a short, let me say, wrap up of the process that you can go now through it and can just try it. I just saw sometimes already the chat popping up, but I could not really read it. So I would close now in principle this section here, and I'm looking forward to your comments, and I will be available until the end to answer some question if I'm able to do so.